Thank you so much for inviting us to ISPD. Anna and I are excited to talk about our open source deep reinforcement learning framework for chip placement. Before we start the talk, we want to thank the collaborators that we had on this work. And if you're interested to learn about our results, please take a look at the paper that we sent to ISPD this year. The name is Scalability and Generalization of Circuit Training for Chip Floorplanning. So we open sourced the method on deep reinforcement learning for placement, which we published in Nature. We open sourced it this year. We call the framework circuit training. And this was a collaboration with Google's RL infrastructure team, which is called TF Agents. And you can check you can check it out at Google Research/circuit training repository. We got a lot of positive feedback from the academic and industry community, and we really hope that this framework would help advance the state of the physical design optimization and other problems in decision making and combinatorial optimization that appears within the chip design stack. So our production flow for using the RL-based chip placement problem is shown in this figure. On the input side, the user will provide the project and the block. We synthesize the RTL and generate a netlist. We do a series of pre-processing before we pass the netlist into an RL macro placer. The RL placer would optimize for placement of both the macros and clusters of standard cells. Once the optimization is done, we freeze the macro placements and pass the netlist through a series of post-processing steps, and then we get the PNR results. And the QOR after the PNR will be the metrics that we would use to evaluate a given placement. So this is the deep RL architecture that we developed for taking an input netlist and placing the nodes of it. On the input side, we vectorize the features of a node, a macro node, such as its its width and height, the adjacency of the netlist graph. We developed an edge-based graph neural network architecture that can basically embed this information in a generalizable way. And then once we have these embeddings, we pass it through a decoder, which basically maps an input node to an XY coordinates on the canvas, which we are placing the chip onto. And another important property is a mask that we have that ensures that at each step of the placement, the policy only places the nodes on legal areas. Here is a description of our distributed RL. We have a number of parallel actors which have a copy of the policy. They run it and they collect the placement reward, and they pass these data to a buffer. On the learner side, the data is sampled and the results are used to optimize the policy architecture, and the new architecture variables are pushed through an experience replay container, and this loop continues until the optimization process is done. Now Anna is will take on from here and talk about some of our results.
Thanks so much, Azalia. Okay, so we wanted to give you a little preview of some of the new results in this ISPD paper. So basically here on this slide, we're looking at what is the scalability of this RL framework? What is the extent to which it can leverage additional compute to get better results? So on the left, we show placement return, which is basically quality of placement as a function of training time and number of GPUs. So each different colored line represents a different number of GPUs that were used in parallel when training the algorithm. And higher placement return is better, and -2 represents infeasible placements. So as you can see, after 8 hours, the algorithm that was trained with 8 GPUs produces the best result, which is unsurprising. On the right, we show the time it takes to achieve a target placement return as a function of the number of GPUs that were used at training. Gray bars here mean that we could not achieve the target placement return with the number of GPUs available. So for example, the best replacement return of -1.07 was only feasible using 8 GPUs. Next slide. So here we wanted to show what is the effect of pre-training and what is the effect of the contents of the pre-training data set, so their relevance to the chip that we're placing at evaluation time. So one interesting observation from this chart is that if you train a model from scratch, it takes about 5 times longer to reach the same placement quality as pre-training, and then testing on the new chip. And furthermore, if you fine-tune or if you pre-train on different versions of the same netlist and then you test on the latest version, you get both higher quality placements and it takes less time, less fine-tuning required. And this is sort of interesting from a production perspective, because it means that in settings where maybe you have multiple iterations of the same RTL, our model could actually leverage those highly relevant prior RTLs to do better at the target task. Next slide. So some other interesting implications for us are, if we have a very fast block level placer, maybe we can use that to do better top level chip floor planning. We could do block shaping, macro selection, pin assignment, and even co-optimizations with earlier stages of chip design, and we're excited about that. Next slide. And finally, we just wanted to say that to our knowledge, this is the first deep reinforcement learning method that was actually used in production to design a system or a piece of hardware. It was used to design the latest 2 generations of TPU, as well as Pixel phones, saving weeks of design time and thousands of engineering hours. We've open sourced our method, published it in Nature, and thank you so much for attending our talk.
Thank you.